In this lesson, we are going to discuss the topic of approximating areas, and which will eventually lead to the conversation and the introduction about and the introduction of definite integrals. At the end of the lesson, in theory, you'll be able to do all of these cool things. But first, let's answer the question, why is area so important? And the truth is that understanding area is one of the central goals of calculus, because it allows us to measure accumulated quantities such as distance traveled or total growth or total change over some interval. And many of these problems can be modeled by finding the area between a graph of the function and the x-axis, and by learning how to approximate and eventually compute such area, we gain a powerful tool that extends far beyond geometry. And for example, the area under the velocity curve gives the total distance traveled, and the area under the probability density curve gives the probability of an event. So in many fields, finding or being able to find the area, it's a crucial skill, and we learn how to do that in calculus. So the problem is set up as following. We have a graph of some function, and in the meantime, we can assume that the function is positive. That means it goes and also continues on the interval from a to b, so it doesn't cross the x-axis. We will relax this requirement later, but in the meantime, this is what we have. We also assume that we are working on some closed interval from a to b, and the task is to find the area enclosed by the graph of this function and the x-axis on the interval from a to b. So this shaded region is what we are interested in finding. And it is pretty obvious that some functions are much easier to find the area under than others. So, for example, if we have f of x equals 2 on the interval from 1 to 6, this one is pretty straightforward. Why? Because it's a continuous function. And when I said continuous, I meant to say constant. And when you have a constant function, the region enclosed by that function on some closed interval is a rectangle. And if we're interested in finding the area of this rectangle, we can use the formula height times base. So in our case, the height is 2, and I made a mistake here. This should be 1. So the height is 2. So this height is 2, and the width is also easy to see. The width is 5. So the area under this particular graph is going to be 2 times 5 equals 10, whatever the units are. So if we have a single rectangle, it's very easy to find the area of such regions. For other functions, we may have to sacrifice the accuracy and learn how to approximate the area using simpler geometric shapes such as rectangles, and sometimes maybe even trapezoids or parabolas in the future. So if we trying to approximate the area, so let's go back to this image and let me bring it over. So if we're trying to approximate the area using rectangles. Now that we made the decision that we're going to use rectangles, the next decision that we have to make is how many rectangles are we going to use. And first, let's learn how to use a single rectangle to approximate the area. If we're going to use a single rectangle, then that rectangle will have the width, which we will label as delta x, equal to the entire span of that closed interval, b minus a, and we still need to construct that rectangle, and there is more than one way of constructing this rectangle. Let me remove these lines, and let's take a look at how many different ways are there to construct a rectangle that spans from A to B. One way is we can use the left value, the output of the function at the left side of the interval, and construct a rectangle using f of A as the height, and approximate the area under the entire graph using this area. Alternatively, let's list all our options. So we can use the left endpoint of the interval. Alternatively, we can also use the right endpoint of the interval. And if we use the right endpoint of the interval, then we're going to be working with this rectangle right here, and we can use the area of this rectangle to approximate the area under the graph. Obviously, it's not going to be exact area, but that's why it's called approximation. Alternatively, we can use a midpoint, so we can find the average of A and B, find the output of the function at that point, and then use that rectangle and its area to approximate the area under the graph. And this method would be, or this selection would be referred to as midpoint approximation. And are there other ways to build a rectangle? The answer is yes, there are. Another way to build a rectangle will be to literally look for the lowest point. If it's a continuous function, it does have the absolute mean by the extreme value theorem, and use that point. So we can use this point and use this rectangle and its area to approximate the area under the graph of the function. And there's no name for this, but we can call it the absolute mean point approximation. And whenever we use or can use the absolute mean, we can certainly also use the absolute max. So similarly, instead of picking the absolute mean, we can also pick the absolute max, which will be this point right here, and we can approximate the area using this rectangle, and then we can call this selection as absolute max point approximation. And notice that if you have a monotone function, then you don't have that much of a choices to make. When you have a monotone function, and monotone function is a function that is either always increasing or always decreasing, if you have a monotone function, then your max point approximation will coincide with the right endpoint approximation, or left endpoint approximation if it's like monotonely decreasing function, and so on. But the point is, even if you're using a single rectangle, you have to be conscious about which of these choices are you actually exercising. And the common ones are left endpoint and right endpoint, but when you're working with certain functions, you can be kind of picky about which method to use, but in general, it doesn't matter as long as you just stick with one. Now, if we use left endpoint approximation, then the area, and we're going to label it as L1. L stands for the left endpoint. 1 refers to the number of rectangles. Then the area will be equal to f of A the height of the rectangle. This is our rectangle built around this value, multiplied by delta x. And similarly, if you're using right endpoint, we call it R1, and then it's going to be f of b times delta x, and for midpoint it's going to be m1, and it's going to be f of the average of a plus b times delta x, and so on. For this one, there's no really name for it, so let's call it a max. We're going to be using the value that produces the absolute max. This one is for the mean, right? And then multiplying it by delta x, and here we're going to be calling it max, and we're going to be choosing the value that produces the max, the largest output on that interval, and building rectangle around that. But this would be what a single rectangle approximation formulas look like. Let's move on and try to approximate the same area using two rectangles. So when you're using two rectangles, we already made decision to use rectangles. We already made the decision we're going to be using two of them. Now we have to make a decision on how we're going to split the interval AB into two parts. In theory, it is possible to, again, become very selective and split it, let's say, like this, unequally, and then use one method here, use midpoint approximation here, and then use the minimum approximation here. In theory, it is possible, and for certain functions and graphs, you may get picky in terms of selecting the width of each interval. But for general function, like without knowing much, we might as well pick the midpoint and split the interval equally. And if that's the case, we introduce the following notation, right? We still have our delta x. Delta x represents the width of each subinterval, and the width of each of this will be delta x. And how do we find it? We compute the total width and divide it by the number of intervals, which is 2. So in our case, the width will be b minus a over 2. And now we can take this delta x and we can repeatedly add it to the beginning of the interval. So we can add delta x to a and then add it again and introduce the following notation. So we're going to call this x0, this x1, and the last point will be x2. So the points x0, x1, x2 collectively are called partition of the interval a, b. And the relation between these values, if you choose to equally spread them out, it will be that the x0 is always the first point. The next one is equal to the first one plus delta x. And then the next one will be equal to the previous one plus delta x, which means it's going to be equal to the 0th one plus 2 delta x, but at the end it will be equal to b. So this is called partitions, and they are easily kind of trackable as long as you know your delta x and the first value, which is a, and then you just repeatedly add delta x to a to produce like those consecutive values. What we need to do next is we need to decide which method we're going to use to create those rectangles. And we can use left endpoint approximation, right endpoint approximation, or mean, max, or midpoint approximation. But in general, we're going to have to pick one or another way some representative in each of the intervals. So in the first subinterval, we're going to pick a representative, and let's going to call it x1 star. And in the second interval, we're going to pick a representative and call it x2 star. And it could be, again, left-hand point approximation, could be right-hand point, could be midpoint, doesn't really matter. We're just going to refer to it as x star. And based on that x, we're going to build a rectangle. And that the area of that rectangle is what we're going to be using to approximate the area of that function on that particular interval. So we're going to be using this area here and this area here. So whichever method you end up using, so I don't know if it's going to be L, R, or M, so let's call it A in general. And 2 here represents n equals 2. A, I'm using letter A for the word area, but it could be L, R, M, or any other letter. In the future, you can use T for trapezoid, S for Simpson's rule, and so on. But for right now, let's just use letter A. And how do we compute A? Like estimate A? In this case, we're going to be using the areas of these rectangles. The area of this rectangle is equal to its height, which is the output of the function at x1 star, times delta x, plus f of x2 star, times delta x. Delta x is a common factor, so we can factor it out. And this is the formula for using two rectangles to approximate the area under the graph of some function. And let's well, let me see if I have a problem that we can try to do now. Well, let's build more rectangles, and then we'll do an exercise. So let's take the same problem, and this time we're going to create some arbitrary n rectangles. So that means we're going to have to create a partition x0, x1, all the way to xn. That's going to be the partition. The width of the distance between these values will be, as always, delta x. So this is going to be my x1, x2. At some point, we're going to get to some arbitrary partition I, whose width is also delta x. And second to last will be n minus 1. And delta x will be equal to b minus a divided by n. Now, for each of this, on each of the subintervals, we're going to pick a representative. So on the ith subinterval, I'm going to pick ith representative. I don't know if you can see it, but I'm writing x sub I star. And we're going to build a rectangle using that representative. So the width of this rectangle is delta x. The height of the rectangle is f of xi star. So the area, the ith area, is equal to f of xi star times delta x. And we can do this for all of these rectangles. So the total area, which we will label a sub n, can be expressed as f of x 1 star delta x plus dot 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 all of them, including the ith, and plus dot 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 the last one. Now this dot 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 is not a pretty notation, so it's not a closed form, meaning it's it could be a mystery what's there behind that dot dot dot. So we use a superior sigma notation to express this sum. So in sigma notation, we're using this symbol. It's called big sigma, and we write the general form of the terms that we are adding, and we also use an index, and the index, which is I, ranges from 1 to n. So this sum has n terms, which is true. 1, 2, 3. This is ith. 4, 5. Not 4, 5, but like whatever comes after I, and this would be the nth term. So that's what this means. And this expression is what we can use to approximate the area under the graph of the function. And then, of course, we label it using letters L, R, M, and then potentially later T or S, depending on the choice of the representative from each subinterval. And this expression actually has a name. It's called the Riemann sum. And the first thing we want to kind of practice is using Riemann sums to compute the not to compute, but like to approximate areas under the graphs of some functions. So this is what those problems are going to look like. So I'm just going to bring some of them here. It explicitly asks you, it gives you a function and it explicitly asks you to use a certain method. So let's just pick a random problem. Let's do 14. Although 12 is very tempting because it's simple. But let's do 14. So our function is 1 over x times x minus 1 on the interval from 2 to 5. So they tell me explicitly how many intervals to use. So I just use this as literally the template, and I do the following steps. First, we're going to draw some function. It doesn't have to be this exact function, so just draw something. The scale also doesn't have to be like super accurate. So this is 2 to 5. We have 6 intervals, so 1, and that's half, and then we divide it into thirds. And then we immediately compute what? Delta x. So delta x will be b minus a over n. So b minus a, in this case, is 5 minus 2 over 6, and that means delta x is equal to 0.5. Now I build the partition, so my first value is 2, and then I repeatedly add 0.5 until I reach my last value. So 3, 3.5, 4, 4.5, and 5. So these are these values: 2.5, 3, 3.5, 4, 4.5. Now it says use L6, so that means we're going to be picking left endpoint as a representative from each subinterval. So that means my L6 is going to be equal to, and now delta x is going to be part of all of them, so you don't have to write it 6 times, you can just factor it out. And here's what I'm writing. Since I'm using the left endpoint approximation, I'm going to find the height of this rectangle by using left endpoint. So it's going to be f of 2 times delta x plus f of 2.5 times delta x, and so on. F of 3, f of 3.5, not enough room, plus f of 4 plus f of 4.5. And make sure you don't get like carried away here and keep writing and writing until you get to f5. f5 is not part of this computation. There should be exactly 6 terms in the parentheses, and f of 5 is not one of them. And and the rest is just putting things in the calculator. So we're gonna plug in f of 2. F of 2 is 1 over 2. F of 2.5 is 1 over 2.5 times 1.5. I don't have a calculator, so I don't think I'll be able to finish this problem. 3 times 2 plus 1 over 3.5, 2.5 plus f of 4 plus f of 4.5 times 3.5 times delta x, and delta x is equal to 0.5. So everything gets multiplied by 0.5. I don't have a calculator, but I'm going to use Desmos. And I don't know if you guys are going to be able to see it. I'll try to bring that little screen here. Actually, I won't be able to see if I block this, but I'm going to type it up in Desmos exactly the way I typed it, exactly the way I wrote it for you here. And just for the sake of finishing this exercise, 1 over 3 times 2 plus 1 over 3.5 times 2.5 plus 1 over 4 times 3, almost there, plus 1 over 4.5 times 3.5, and all of that we get multiplied by 0.5. So I'll show you what I got here. I literally just put it in Desmos. Desmos computed it somewhere here. Let's see, there you go. So using this method, we approximated the area under the graph of this function as roughly 0.597222. Is it accurate? I don't know. We are not concerned with accuracy yet. We're just concerned with the skill of creating these Riemann sums and using them to approximate the area. So in summary, what are we capable of right now? We can build a Riemann sum given a number or the value n that determines the number of rectangles, and also assuming that we know how to pick a representative from each subinterval, and then we build this formula. So what's next? You, maybe me too, but we will spend more time in Calculus 2 analyzing and comparing the errors and the efficiencies of each of these different approximations. But intuitively, right now, it is obvious that the larger the value of n, then the better the approximation can become, potentially. So, therefore, if one is looking, and we were looking, right? We started the class by asking the question on how to approximate the area under the graph of the function. So if we are looking for the area, then we must we must aim for building the Riemann sum with as many rectangles as we can. And what's the largest n we can do? Well, 1,000, 10,000, 1 million. The answer is, earlier we learned how to send values to infinities if needed. And this is the time when we actually do need it. So if you are looking for the area, you must consider finding or computing the limits of Riemann sums. And if such limit does exist, regardless of how representatives are picked on each subinterval, then such limit must be equal to the area that we're looking for. And furthermore, when the area that we're looking for can be found using the limit of a Riemann sum, we call this function integrable. And not integrable, but integrable in the, like, on the interval from a to b. Function could be integrable on one interval and not integrable on another interval, but to be integrable simply means to have the finite area that can be found using the limit of a Riemann sum. And anyway, when this happens, when this is the case, so the area exists and it's equal to this limit of the Riemann sum, we call this function integrable, and we introduce the following notation. We say the integral from a to b of f of x dx is equal to the limit of the Riemann sum as n goes to infinity. This integral is called definite integral notation. Definite as the opposite of indefinite. The difference is definite integral has limits of integration. So these values a and b are called limits of integration. But everything else is the same. Everything in between the integral symbol and dx is called integrand. And this is the variable of integration. Technically, it's not really a variable, it's just a placeholder. So sometimes it's referred to as dummy variable, because the area under the graph of the function would be the same regardless of which letter you used. So technically that variable doesn't really serve the purpose of a variable. What else are we missing here? This is, as before, it's called the integral sign. And that's it. So this is what we call the definite integral. The good news, well, before we get to the good news, the one thing we have to practice is recognizing Riemann sums when we see one. Not a good picture. Let me take another one. Oh boy. So let's take a look at some of these exercises here. So this is what limits of Riemann sums look like, and when you're looking at one, you got to be able to identify which function are we dealing with and how to turn this limit into the integral. So let's do number 17. What do we have? So we need to recognize this pattern. We have a limit of a sum of a function delta x, right? So whatever in between the sigma and the delta x will then become the function. I goes from 1 to n goes to infinity. So this is our function right here. So this in question 17 we have integral from 2 to 6 of x ln 1 plus x squared dx. So we're looking for the area under the graph of whatever. I don't know what it looks like, but whatever it looks like, this Riemann sum represents the area between 2 to 6 under that graph. Similarly, like I'll do, let's say 20, right? And you'll do the rest. This will be based on the pattern integral from 1 to 3 of x over x squared plus 4 dx. And whatever that graph looks like, this integral represents the area from 1 to 3 under the graph of that function, assuming that function is positive. I actually don't know. It should be. It should be. Because that's assumption we've made earlier, and we haven't relaxed that condition yet. So that's one skill. Now, back to the good news. The good news is that I'll copy it here. The good news are that all continuous functions are integrable, and therefore we can focus on finding the area rather than worrying about the existence of the limit. So most of these problems, again, so we had a big if when we defined that definite integral. That big if was if that limit exists, regardless of the representatives. Now, this statement tells us that that limit will exist for all continuous functions, and we don't have to worry about the existence. Now that we know that, we can now focus on actually finding the area. So let's take a look at this problem. And let's find this integral. So to find this integral means to, I don't need to copy it, but to find this integral means we're looking for the area under the graph of this function. What's the graph of this function look like? So if you draw something like generic and write it like this, the way we did it before, you won't be able to find this area. So you have to be a bit more specific. Although I do know what this looks like, I'm going to open up Desmos, and I'm going to graph that so you can see what it looks like. Oh, while I'm typing this, you can also graph it yourself. 9 minus parentheses x minus 3 squared. So the graph of the function that we're looking, the area under which we're looking for is this. So not what we drew, but this right here, right? And what does that mean? That means if we know this area, we know the answer to that question. Actually, not this area, sorry. Because the integral is from 3 to 6, we're looking for this area. Right? I don't know if you can see it. But this is a simple geometry. So the area of a circle is pi r squared. So the area of a circle of radius 3 will be 9 pi. We're dealing with a quarter of a circle, so we're looking for the fourth of that, and we found it. So this area right here is equal to 9 pi over 4, and that's it. Now, I don't recommend doing this too much, but I'm actually going to type this integral into Desmos. Believe it or not, Desmos is pretty good at finding definite integrals, and I'm going to show you the result right now. 9 pi over 4. So this is what we got by typing this to Desmos. So to confirm that we got the right answer. And we got this skill of being able to compute some of these definite integrals by simply understanding that definite integral represents the area. Now, I'm not going to do this, but I'm going to ask you to do this real quick. so what I want you to do is to draw this image of the graph by hand, and then find the area under the graph of this function on the interval from 2 to 4. So I'm going to, let me see if I can get fancy here with x between 2 to 4, so 2 less than x less than 4, and we're going to draw this. No, that didn't work. How do we make it less? Huh, I don't know. But here's the graph of the function. And to find this area, you simply have to kind of use some geometry. So you have to look for this, the area of this trapezoid, and the area of trapezoid, just so you know, it's equal to AB if this is height, so it's going to be A plus B over 2 times H. So in our case, this is one of the, if you put it sideways, this is going to be 7, this is going to be 11, so we have 7 plus 11 over 2 times height, and the height of the sideways trapezoid is 2. So it's, the answer is 18. And I'm also going to type this exact expression in Desmos. So integral from 2 to 4 of 2x plus 3 dx, and you have to type parentheses there, is equal to 18. So I'm going to show you all the code I generated here in Desmos, so you can play with it yourself. This is what we get in Desmos. So we found the integral. Congrats, right? So we are doing something very, very meaningful using the notation that we just learned. So it's called definite integrals. Now that we've been assured that integrals do exist, regardless of the representative, why pick a representative to make things harder when you can pick a representative to make things simpler? So in general, like, we can just pick the right endpoint representative and simplify the formula for computing the integral to simply become, instead of using that star notation for representative, you know, once you settle on the right endpoint approximation, you're just always picking that xi. So you don't have to put that star symbol there. This will give you the same exact answer. So using, this is a Riemann sum, using right endpoint approximation as n goes to infinity. Now, in order for us to, you know, take advantage of this formula and see some examples, we do need to kind of familiarize ourselves with properties of sigma notation. So I'm gonna just throw it out here, and hopefully you are already familiar with these properties. If not, then it's not a big deal, because definite integrals do inherit a lot of these properties, so sooner or later you will know them, if not directly, then indirectly. But this is some of the properties and facts that one is expected to know when it comes to sigma notation. To go really quick through the list, sigma notation possess linearity property, meaning that sigma of a linear combination is a linear combination of sigmas. Some interesting property here is the reindexing property. You're going to need this in when you study power series or series in general in calculus 2. So you'll come back to this eventually. But reindexing is like a nice property that is worth kind of knowing. So if you're trying to reindex your sequence series, sigma, for whatever reason, then this is how you do it. And this is also an important one. You can split or subdivide your sigma into two sigmas by just kind of dividing it somewhere in the middle. So instead of running from 1 to n, you pick some value k and you run from 1 to k, and then you pick up the next element after k, which is k plus 1, and you run through the remaining of the sum. And some of these formulas are also important to know, but we can treat them as identities, right? So I'm not going to derive them for you. We're just going to treat them as well-established facts. And what can we do with this? With this, we can now take a simple, and let's not even reinvent the wheel. Let's just take the same problem. Integral from 2 to 4 to x plus 3. Integral from 2 to 4 to x plus 3 dx. And we're going to use limit of a Riemann sum to find this integral. So it's a limit of a sum. I goes from 1 to n as f of xi times delta x. Delta x we know is equal to, I'm going to pretty much just start throwing things inside, right? We still have sigma, but my f is 2x plus 3. So I'm going to plug in 2xi. Actually, hold on. It's not going to be xi. Before we start plugging in things, let's actually draw a picture. Let's create the partition. We have the following image. We're going from 2 to 4. This is my x0. This is my xn. Here I'm going to pick some ith subinterval. So this is going to be my xi minus 1. This is going to be xi. And this is going to be my delta x. And because we're using right-hand point approximation, I'm always going to be picking x sub I. And I'm going to start with x1, and I'm going to end with x sub n. But we're going to evaluate the function at xi, and then we're going to build a rectangle, and then we're going to find the area of this rectangle, and then we're going to add them all up. The one thing I need to do here is I need to express delta x as b minus a over n. B minus a, in my case, are not some hypothetical values. They're actually given. B is 4, a is 2. So delta x is 2 over n. And we also need now a formula for xi. Xi is, according to our previous discovery, is equal to a plus I delta x. So in order for us to get to xi, we have to add delta x I times. So using our numbers, we plug it in. A is 2, I is I, and delta x is 2 over n. So that's my xi. So I'm not just plugging in xi in here. I'm actually plugging in this value. And now we're ready to plug things in. So we have limit as n goes to infinity. Sigma I goes from 1 to n. F is 2x plus 3. So into this 2x plus 3, I'm going to plug in xi. But instead of xi, I'm actually going to plug in this. So we have sigma I goes from 1 to n. And now we go 2 times xi, which is 2 plus 2i over n. A lot of 2's there. So that's my xi plus 3. And we multiply by delta x, which is 2 over n. And before we get to compute this limit, we need to figure out this sigma. So let's focus on what's inside sigma. So we have 2 times 2 plus 2i over n plus 3 times 2 over n. And let's simplify. So let's distribute that 2. So we have 4 plus 4i over n plus 3, so that's 7 plus 4i over n times 2 over n. So we have 14 over n plus 8i over n. That's what's inside of my sigma. So when you apply sigma from I1 to n to 14 over n plus 8i over n, we're going to end up with, it's actually n squared here, right? So we have 8i over n, so this is n times n becomes n squared. So this is n squared. And now we're going to be using properties of sigmas. So we have 14 over n, we're using linearity, so we take out 14 over n. N is a constant, so we can take it out, and we have 1 over here. Plus, we take out 8 over n squared, and we have sigma of I. So pretty much you can take anything out except I. And now we're going to look back here, and again, we're looking for this and this. So the sigmas of bunch of 1s is just going to be 1 times n, n. And the sigma of I is going to be n times n plus 1 over 2. That's a well-known formula. So we plug those results in. So here we get n. And here we get n times n plus 1 over 2. And this simplifies quite nicely. So we have 4n plus 1 over n. So that's what sigma, so we don't have sigma anymore, we just have this expression right here. And little by little, we kind of figured everything out. We first figured out what's inside of sigma. We now computed sigma, and now it's time for us to find the limit. So we're continuing with the limit. So we have limit as n goes to infinity of 14 plus 4n plus 1 over n. And even though it's not a continuous function, but rather a limit of a sequence, it's not hard to kind of assume that it works the same way. And the limit of this rational expression as n goes to infinity is just 4. And the final answer is 14 plus 4, which is what? 18. So we were able to find the same integral, but instead of using the graph and geometry, we used the limits, or the limit of the Riemann sum. And this particular exercise can be performed for linear functions and quadratics. We're kind of limited in terms of what we can do using Riemann sums easily by these formulas. So if you see a problem like this, I would suggest maybe YouTube a couple more of this just to see like someone else doing it, and then try one yourself. But the point is, the answer that you'll get from using the Riemann sum is exactly the right answer, like that we're looking for. So you can trust that Riemann sums actually work. Okay, so let's move on. Now that we understand that the definite integral of a positive function on the interval from a to b is the area under the graph, and now that we have seen some examples of computing the integrals, maybe not plural but singular, but we have seen example, we can now list all the properties, not all the properties, some of the properties of definite integrals, and here they are. Because integrals, as you could see, arise from finding, definite integrals arise from finding the limits of Riemann sums, it is not a coincidence that the properties of definite integrals overlap a lot with the properties of sigma notation. And here they are, side by side. Okay? What does this mean? That means when we have an integral of a, in other words, constant can be taken out of the integral. integral of a sum and difference can be split into sum and difference of integrals, and an integral of a linear combination is a linear combination of integrals. And subdivision property works nicely, something that indefinite integrals don't have, just simply by the nature of being indefinite integral, but definite integrals do have, like, it's the subdivision property. So you can divide the area. Let me draw the picture actually. So pretty much subdivision says if you have the area from A to B, which is what we expressed with integral from A to B, and you can pick some value C, and if you do that, then this area now is expressed by integral from A to C, and this integral, or this area, is expressed by using integral from C to B. So if you look back to that property, it says the total area from A to B is equal to the area from A to C plus the area from C to B. Duh, right? So it's like, this is your area from A to C, and this is your area from C to B. Of course, together, it's the area from A to B. So subdivision property makes perfect sense in the context of definite integrals. Now, everything that we have done so far was done assuming that we're working with a graph of a function that is above the x-axis. In other words, a positive function on the interval from A to B. So what will happen if we attempt to find the integral of a function that is not always above the x-axis and may go above or below? So let's consider the following example, and let's answer the following question. Consider this function on the interval from 0 to 5. What exactly does the integral from 0 to 5 represent? Is the question, and let's find out. Without graphing this integral, or rather graphing the function, we do not graph the integral, we graph functions. But without graphing, I can assume that by subdivision property, the integral from 0 to 2 together with the integral from 2 to 5 should be equal to the integral from 0 to 5. Right, that's the subdivision property. Now, if you do graph this function, what you'll see is that, well, we should be able to graph this. This is a linear function with the y-intercept -4. So 1, 2, 3, 4. Slope is 2, so 1, 2, and we go from 0 to 2. So this is 2, 2, 2, 5, right? So this is the graph of this function. And all right, so what do we get? There's definitely no confusion about what this represents, right? So that must represent this area. So that's for sure, right? So the only thing that we don't understand is what is this, and therefore what is this? So what is this? What is this is the question that we're trying to answer. And if you set up, we're not going to do that, but like if you set up this integral as a limit of a Riemann sum as n goes to infinity, and you do all the math the way we did it earlier, and you will see that the answer is going to be -6. How? Why? How could it be? Well, what this means is that -6 cannot be the area, because area can only be positive. So it's not the area. What is it then? And in order for us to make sense of what we're seeing here, we have to introduce the new term. And we introduce this term, it's called the net area. So the new term is the net area. And the introduction is as follows. When the function is positive, on some interval, the net area coincides with the area between the graph and the x-axis. So when f of x is positive, no issues. When f of x is negative, the net area is actually the opposite of the area between the graph of the function and the x-axis. So again, according to this definition, what we see is not the area, but it is the net area, and net area is the opposite of this area. So this is geometric area that we see, but the net area is the opposite of it, so it's -6. This is the area that we see, so it's from 2 to 5, 3. The output is at 5, 10, 6, so 3 times 6, the area is 9. And the net area here coincides with 9, so net area is +9, net area here is -6. That's how we define the net area. And if the function goes up and down or above and below the x-axis, then the net area represents the difference between all the positive areas and all the negative net areas on all of those sub-intervals. So that is the answer to the question, what does the integral from 0 to 5 represents? It's the net area as the difference between the positive net area and the negative net area. So it's not the difference, it's actually the sum, clearly, right? So this is going to be -6. This is going to be +9. So the net area is +3, meaning there's 3 more square units of positive area than it is. I should say there's 3 more units of the area above the x-axis than it is below the x-axis. So that's what it is. That's what it means. And if you look at the graph of this function, you can see it does have a larger... My microphone just fell. Let's see. All right. So let's update the interpretation of a definite integral. Definite integral is the net area between the graph and the x-axis, now that we know what the net area is. And that means it's okay for the integral to become negative. So that's the big kind of takeaway from this. Yeah, I don't know. Anyway, this is kind of the main takeaway. Integral from a to b is not the area, it's the net area between the graph and the x-axis. So we don't use the word under anymore because we're not necessarily dealing with the positive function. So when you're working with the positive function, we use the term area under the graph. Now that the function could be positive or negative, right? We don't use the word under, we use the word between the f of x and the x-axis, right? So the net area between the graph and the x-axis is exactly what this integral represents. Now, luckily, removing this condition of a function being positive didn't result in any issues in terms of properties. Properties previously listed are still valid, even with the negative outputs, and we can even add more properties. But before we add more properties, while we are still on this graph, I want to add another fact. So if the integral of the function represents the net area meaning it could be positive, could be negative. If you are still interested in the total area, so if you're interested in adding this together, treating this as positive and treating this as positive, so if you're interested in treating both of this as geometric areas, then you simply have to set up the integral of the absolute value of the function. So it's going to be total geometric area. So net area versus total geometric area, not the same thing. Now that you understand that, let me list. I'm not going to list them. I'm just going to copy and paste it here. Let me list some additional properties. Here's one. Let's take a look at what it says. It says if you integrating a function from a to a, the answer will be 0. Why is that? That's because line segments don't have areas. Integrating a function on the interval created by a single point doesn't give us the second dimension. We're still in one dimension, and one-dimensional objects don't have areas. So the area is 0. So one consequence of this is probability of a continuous random variable being equal to any particular value is always equal to 0. So that's because of this property. The other property is if you, for whatever reason, accidentally wrote integral from, let's say, 5 to 1 instead of 1 to 5. So when you're writing your upper limit, higher value in the lower limit and the smaller value in the upper limit, you're essentially doing integration instead of left to right, right to left. Because in the formula, we subtract a from b, not b from a, right? So in the formula in the Riemann sum, let me scroll here, right? We subtracting a from b, not b from a. So when you're trying to plug the higher number into this formula, the answer will be negative. So the point is, integrating from right to left, it's not a crime. You can do that, but you're just going to end up with the opposite of what you're looking for. So usually what we do, we just flip the limits of integration to be the lowest on the bottom, the highest on top, and we just put the negative sign in the front to account for that negativity. Okay, so that's one list of properties. Another one is pretty cool. I'm just gonna throw it out there. I'm just gonna write it. It's a short one. So if you're integrating a function on a symmetric interval, meaning it looks something like this, right? Let's say we integrate parabola on the interval from -2 to 2. Well, parabola has a nice property of being symmetric with respect to the y-axis. So sometimes instead of integrating from -2 to 2, we say, well, I don't need that. I know it's going to be same area to the right as it is to the left, so I'm just going to find one of them and multiply it by 2. So what it means is when your function is even, we sometimes just integrate from 0 to a and multiply it by 2 instead of integrating from -a to a. On the other hand, when you're doing the same thing, meaning integration on the symmetric interval, for an odd function will be a function like x cubed. What's going to happen? Well, you can see same thing. According to the symmetry, this geometric area will be the same as this geometric area, but guess what? This net area will be exactly the opposite of this net area. So whatever you have here with plus, you're going to have here with minus, so everything will cancel and the answer will be 0. So we summarize this property with the following statement. If you have integral on the symmetric interval around 0, then it's equal to twice as much integrating from 0 to a if f is even, and it's equal to 0 if f is odd. So pretty cool. The last thing, I'm just gonna literally copy it from the book and throw it out here. We're gonna need this to prove some theorems in the future. So these are called comparison theorems or inequalities involving integrals. So it pretty much says If you have a positive function, integral of a positive function will be positive. Makes sense. We can even say more than that. We can say integral of a function that's more on the positive side will be positive, because the area, if the positive area outweighs the negative net area, then the net area will still be positive. The next one says that the integral of a bigger function is bigger. Makes sense, right? So the area, if you have two functions and one function is, let me see if we can change color. If we have two functions, g and f, and we consider both of them on the same interval, if this is integral of g and this is integral of f, then you can see that integral of f is greater than integral of g. Why? Because f is greater than g, so the area must be greater. And finally, the last one says, if your function is bounded between some values, so if as it gets as big as m and as low as lowercase m, then using rectangle build at the largest value will overestimate the area, and using the rectangle build around the value that produces the absolute mean will underestimate that area. So the area that you're looking for will be in between the lower bound estimate and the upper bound estimate, which is what this says. This concludes the lecture, the introduction to definite integrals. If you have any questions, let me know when you see me.